Welcome to Learning with Philemon. In this video, we will not be looking at anything in the GCSE, IB, or A-level curricula, but instead having a bit of fun and exploring some university-level chemistry in the Star Trek universe. I'm very excited that the 5th season of Star Trek Discovery is coming out soon. I must admit that I'm still on season 3, but I'm glad that there's more to look forward to. I hope the Trekkies out there will enjoy this video. In the Star Trek universe, ships are able to travel way faster than the speed of light, allowing them to explore the universe. How the ships are able to manage this is actually partially based on real science. The ships have a warp core, which is essentially a reactor of antimatter and matter. When antimatter and matter come into contact with each other, both are annihilated, producing a large amount of energy. If all the matter-antimatter reacts at once, this would cause a huge explosion, destroying the ship and a vast area of space around it. You could compare this to an uncontrolled chain reaction in a nuclear power plant. To control the reaction, dilithium crystals are used. These crystals have fictional magnetic properties that trap the antimatter close to the crystal without actually touching it. This is necessary because if the antimatter touches the crystal, it would destroy it, and then any part of the ship it would get in contact with. The crystal confines the antimatter and directs it to react with only the required amount of matter. The dilithium crystals act like the control rods in a nuclear reactor. In Season 3 of Discovery, we found out about the burn, where all dilithium became inert. This led to all active warp cores detonating. Now let's have a look at the chemistry behind dilithium. A dilithium molecule, Li2, consists of two lithium atoms bonded together. Lithium has an electron configuration of 1s2, 2s1. This means that it has 2 electrons in the 1s orbital and 1 electron in the 2s orbital. For more on this, please watch the orbitals and electron configuration videos. When two atoms form a covalent bond, their atomic orbitals overlap. For example, when the two 1s orbitals of the two lithium atoms overlap, a bonding and an anti-bonding orbital are formed. In the bonding orbital, the electrons can occupy the space between the two nuclei, denoted by the black dots. Both positively charged nuclei are attracted to the electrons, which holds the nuclei together. This also lowers the energy of the bonding orbital compared to the individual atomic orbitals. The molecular orbital is called sigma because the atomic orbitals overlap along the internuclear axis. For more on this, please watch the video Molecular Orbitals, Sigma and Pi Bonding. When the two atomic orbitals overlap, an anti-bonding orbital is also formed. In this case, the electrons cannot occupy the space between the nuclei. There is no attractive force to hold the nuclei together. Instead, the two positively charged nuclei repel. Whether two atoms can form a stable molecule depends on the balance of attractive and repulsive forces, and hence the number of electrons occupying the molecular bonding and anti-bonding orbitals. To visualize this, we must draw a molecular orbital energy diagram. In this diagram, we see that the 1s and 2s atomic orbitals combine to form two bonding and two anti-bonding orbitals. Note that the bonding orbitals are lower in energy than the atomic orbitals, and the anti-bonding orbitals are higher in energy than the atomic orbitals. According to the Aufbau principle, electrons should fill the lowest energy orbitals first. We have 6 electrons available from the 2 lithium atoms. Starting from the bottom, we will fill these orbitals. 1, 2, 3, 4, 5, 6. The attractive force from the first filled bonding orbital and the repulsive force from the first filled anti-bonding orbital cancel out. However, we have 2 electrons in the second bonding orbital. This means that overall there is enough attractive force to keep the two lithium nuclei together. In fact, the bond energy of dilithium is 110 kilojoules per mole, which means that 110 kilojoules of energy is needed to break the bonds in 1 mole of dilithium molecules. This diagram proves that dilithium is in fact a stable molecule. Unfortunately, dilithium does not have the magnetic properties required to confine antimatter. However, I have linked in the description an article describing the development of a fusion reactor using deuterium and a compound consisting of 6 bonded lithium atoms. So who knows, maybe in the future we will be able to travel at warp speed. Thank you for listening. If you haven't already, please subscribe for more content. Live long and prosper.